A 50-kilogram sprinter starting from rest runs 50 meters in 7.0 seconds at constant acceleration. Part A, what is the magnitude of the horizontal force acting on the sprinter? So the first thing that I want to look at is just what we know, and also draw a model in order to get a good understanding of the problem. So the problem is asking specifically about horizontal force. So while I have indicated normal force and gravity, which are going to be pretty weird in a running situation, we can kind of just ignore them and just look at that horizontal force, the force of the track on the runner. And that is actually a reference to Newton's third law. That horizontal force is on the runner is actually caused due to the fact that the runner is exerting some force on the track, and because of Newton's third law, which states that everything has an equal and opposite reaction, the track is going to then exert some force on the runner, which is going to allow them to accelerate. So that is where that force comes from. So the problem is asking about that horizontal force. And we know from Newton's second law that force equals mass times acceleration. And while we do have the mass, we don't know acceleration yet, but we have all the information we need to solve for it pretty easily. So we can just use one of our kinematics equations. Distance equals 1/2 at squared. And then once you do some algebra to isolate the acceleration and plug in your numbers, we just get that the acceleration is going to be 2.04 meters per second squared. And that's going to be the acceleration for the runner from 0 to 7 seconds. That acceleration is constant, which is going to be something that is going to be useful for us in part B. But the problem is asking about force, and we can just do some really simple math and get that the force is 102 newtons. Also notable that force is also going to be constant, which similarly is going to be useful for part B. So part B is asking about the sprinter's power output at 2, 4, and 6 seconds. So there are several ways to solve for power. Probably the most simple one being work over time, because that's pretty related to the definition of power, which is the energy output over some amount of time, basically. But power, we were given this unit that power also equals force times velocity. And although I didn't show it here, that is true, and you can see it really clearly by just looking at how the units work out to actually equaling watts. But yeah, I use this equation due to the fact that we are given the time aspect, and we also already know the acceleration. And since we know from way back when in the kinematics unit that those have a relationship, we can equate acceleration times time to the velocity and plug that into the power equation, giving us that power also equals force times acceleration times time. And that's going to make our calculations really, really easy. And you can see that on the right, where I just used that force that we previously solved for, 102 newtons, and multiplied it by the acceleration we previously solved for, 2.04, and then you just multiply it by the seconds that the problem provides. And so at 2 seconds, the power is going to be 416 watts. At 4, it's going to be 831, and at 6, it's going to be 1244. So that's basically the end of the problem. The one thing that I wanted to point out that can be a little bit tricky at first is there are multiple paths you can take to solve this problem. For me, I didn't realize right away that it could be as simple as replacing that velocity with acceleration times time. And I went ahead and went through a long process of solving for distance and then using that distance to solve for velocity at every point, at every time that we were given. And it's just really, really time consuming. So I'd say always look out for shortcuts like this. That will make the physics much faster and easier. So yeah, that's the end of the problem. Thanks for watching.